So today's talk will be on key management, so operationalizing cryptographic key management for regulatory compliance as well as emergency incident response. I'll quickly run through the agenda for the talk. I'll talk about the current landscape, regulatory shifts, and in the context of incident response as well, security incident response, and the SREs, take the SRE perspective on this. I'll quickly have a crypto 101 just to ensure that the terms I'm talking about are clear, and I'll be focusing more on the challenging aspect of asymmetric keys here. Then we'll quickly dive into the design patterns for building these pipelines, for automating them and decoupling them from some dependencies that might be challenging. And we'll also look into how we can run these key changes with high availability in mind, tiered SLOs, and make sure that the architectures are audit ready as well. We'll also look into leveraging the same infrastructure for dual purpose, so to speak, for compliance as well as emergency response, like I said. And we'll have some time for Q&A. So jumping into this, so the context in the context of emergency response, you might have seen it's a matter of when, not if. In the past few years, we've seen a bunch of incidents where there was a crash dump or some of the way a key was compromised, and then there's this attack surface for a few hours or probably even weeks sometimes, and the attacker is able to get access to the assets that this key could unlock. Today, there's a lot of systems that were not built with this kind of attack patterns in mind, and there's an agility gap here where incident response takes order of weeks sometimes because key rotations were not kept in mind with security in the design when the design was built. And we also need to make sure these high-risk operations are not just fixing the security incident, but also make sure that reliability is kept in mind, availability kept in mind, and this means that we need well-tested pipelines that are not just tested in production, so to speak, when there's an incident, right? The second context, which is now newly showing up, which I was a part of, that was mentioned, is sovereign cloud. So we're seeing a lot of traction in some of the geographical regions where there is a need for sovereign cloud development, so to speak. Think of it as a cloud that operates pretty much within that particular geographical region. So there's a regulatory shift here where modern frameworks demand provable compliance, so to speak, than just having key management for security. So you need audit-ready pipelines, and SREs might provide audit trails, making sure that they can demonstrate who holds these keys and when they change, the timestamps and everything. So these cryptographic workflows are not solved just by traditional KMS tools, and we'll look into why. And so this needs to be kept in mind when you're building these key management pipelines. All right, I'll do a quick run through of what key management and rotation means here. So when we're talking about key management, this is talking about the full life cycle, where you're generating a cryptographic key, whether be it a signing key or an encryption key. You add the key, and then there is the storage aspect involved. And with asymmetric keys, we also think about distribution of the public key. And we're also talking about the deletion of the key once it's no longer in use. When we're talking about rotation, this is retiring an existing key that is actively in use. So we're talking about a key that's used for signing, it's still used in production, or key that's used for encryption. And we're trying to retire that in favor of a new key that's been added. And we're basically limiting the exposure in case there was an incident, or in the case of meeting some compliance standard, making sure the key in use is recent enough. And now I'll quickly talk about why I just mentioned that the asymmetric keys are challenging. Right? So there are two types of keys fundamentally. There are encryption keys and signing keys. So when we talk about encryption keys, these are symmetric keys. So what this means is there is just a single key that is used for both encryption and decryption. So generally easier to manage, so to speak, because think about a storage device that you're using a key to encrypt the data on disk. So a service encrypts the data, writes it to disk, and when you're trying to read the data, you decrypt the data with the same key and then read the data, right? So generally easier to manage, often handled within a KMS. Whereas asymmetric keys, on the other hand, it comes with a key pair. So you have a private and public key pair. So the private key is used for signing, and that's often guarded somewhere securely, not accessible to everyone, but only the signing parties, and probably even hardware backed in a root of trust. So typically just accessible only to the signer. Whereas the public key verifies the signature. So this must be widely distributed. All the parties that need to verify these certificates that were signed with the private key need access to the public key. So these are used by a lot of production critical service identity keys. So when you think about a service that needs to prove that it is indeed running as identity it is claiming to be, so it shows a certificate and that needs to be verified by another service that is talking to this. So these are usually production critical. And the rotation gap with the asymmetric keys is indeed this part, really, where the public key needs to be distributed before you can switch over to the private key. Switch over a new key in the private key. So this is the public key distribution problem is what makes it more challenging for the asymmetric keys. Looking into the scenarios where these key rotations are usually taking place, right? So we have three modes usually. So you're talking about hygienic rotations. So when you talk about hygienic rotations, think about periodic key changes. So you have some compliance mandate that you're trying to meet, and the keys need to be of X age to meet that standard, right? So you cannot have a key older than, say, 6 months. So this means that you need to make sure that there are periodic rotations happening so that you can meet that compliance standard. So that's what hygienic means. And emergency is what I just talked about a few minutes back, which is rapid emergency response to a security incident. So an active key in use has been compromised somehow, and you're now trying to rotate it out to a new key. And then there's this external requirement that might come in with data sovereignty that's showing up these days, which is basically when they want you to demonstrate a key rotation so that you can prove to them that the keys are now in control of a party that they trust. Right. So in all these cases, there are SLOs that need to be kept in mind in terms of availability, speed, and verifiability. So when we talk about availability, it is a little bit varied in the context of the three different types of rotations. When we say hygienic, this is a fully serving production fleet, right? So typically, you don't want to be running a key rotation like an incident in that case. So we are looking at high availability here. It should be any number of 9s that you usually have in production, and typically should be just invisible to the services that are running there. They should just run like they do, whether or not there's a rotation happening. Now, emergency, on the other hand, is a little more tricky because availability here can be so non-critical services could technically be affected in terms of availability here. So the SLOs need to be tiered in some sense, but I'll also dive into that a little more in detail in a few slides. Speed also changes a little bit with respect to hygienic and versus emergency rotations. So hygienic is more deliberate, slow rollout type of rotations, versus emergency is obviously speed to safety. So that's where the SLO for speed is going to be different for the different rotations. Verifiability typically is pretty much the same throughout the three. You want to be audit ready. You want to be able to ensure that the security incident is indeed resolved, so you need metrics for those as well. And we'll look into what those metrics should be in a bit. So I'll quickly jump into a few design patterns that usually work for particularly asymmetric keys to make sure you have a pipeline that can satisfy these requirements. So the first pattern is about certificate rotation, right? So when I was talking about these asymmetric keys, you have these certificates that are generated, and you must be able to rotate those certificates frequently enough in order to be able to rotate the root keys that you're using to sign those certificates. So for this, you want to decouple the rotation event, the certificate rotation event, from servers and hardware dependencies. So there are a few design traps that can make this complex, right? So the first one being long lifetime of the certificates. So if the certificates, let's say, doesn't expire for like years, right? If you have an very long expiry, so that's going to be difficult to rotate because services are now running under the assumption that these certificates are probably not going to expire in X years. So when there is an incident, the service is not ready to take that rotate. Either you're not able to rotate it, or it's going to break that service because it's running under that assumption. So the solution is to deliberately reduce that expiry time and make sure services are able to adapt to that. And so the best strategy here is to make sure the services are having a periodic pull model where they are able to refresh the certificates periodically. And in an event of emergency, you can push a button and make sure that the rotation event happens seamlessly, right? The second trap is hardware binding of keys. So traditionally, there has been the way of distributing public keys at the hardware level when you have some service running in the firmware layer or things like that. Baked in keys in the firmware is tying you to long hardware deployment cycles. So if you want to change those keys, that means you're going to actually have to flash the firmware again on a hardware. And so that's going to make life difficult if you want to rotate those keys out, right? So avoiding embedded keys in firmware binaries is the way to go, and potentially using late binding to inject the keys later on in the life cycle so that it's online, so to speak, versus like tying yourself to hardware deployment cycles. The last one is hitless updates, so preferring hitless updates. Again, traditionally, cert rotations sometimes require a draining of a machine or draining of a device of the jobs that are running on that, and then potentially even restarting the machine, reinstalling the machine, restarting processes, which can be expensive because you'll have to do migrations. So designing cert rotations in a way that they are hitless is also critical here because machine and device certificate updates, if they're not hitless, you're going to have to wait far longer than necessary especially for emergency response. All right. The second pattern is to have an automated pipeline and make it state-driven so that this can be pretty much used for all kinds of key rotations that we just talked about. So in this picture that you're seeing, the top boxes are all state transitions of a key, and the bottom, what you're seeing, are the monitoring signals that go into it. I'll quickly run through a quick key rotation right over here for an asymmetric key pair. So let's say we are switching over from key pair A to key pair B. So the production is now using signing key A and verification key A correspondingly, and the signer is using A verifier as well. So the certificates that are in production are on the key A, are signed with key A. And now we want to rotate over to key pair B, all right? So we're now trying to add the key. You need to have monitoring metrics in your KMS or whatever generates these keys to check whether this key is now ready to be used. At this point, you want to first start distributing the new public key to your verifiers. So you start pushing the keys to your verifiers, which now trusts both the signing key A as well as the signing key B, the verification key A and the verification B. And at this point, the signer is still on the previous key A, so which means that the certificates in the fleet are still on the signing key, are signed with the signing key A. You need to first verify that there is full distribution, which means that all the verifiers have both the public keys in their trust bundles. And once that has happened, you can now pivot over to the new signing key in the signers. So now the signers are signing with the new key. At this point, you can say that, when you're looking at the metrics, you can now say that you're now only using new keys to verify signed certificates. And the fleet now has certificates that are signed with the new key as well. So this is a gradual process. You need to wait for all the certificates to rotate over to the new key. And you have monitoring signals to verify that all the certificates are fresh, which means they're all signed with the new key. And now you can distrust the old key, at which point the verifiers will all now only trust the new key B. So here, if there's an incident where A was compromised, you're no longer trusting it. which means the attack is moot at this point. And now you can obviously delete the old key pair in your KMS wherever else it's been stored. So if you see, the key features here are that it's state-driven. You need to make sure you have databases that track the key state, and also monitoring signals from both the signing side and the verification side to be able to make these state transitions easily. And also this needs to be predictable and idempotent, so to speak. So there is no half-baked progress of a step. So despite doing all this, there is a potential for incidents here, right? But we need to be prepared to handle those incidents. So the usual scenarios where it's a large enough incident is premature change of the keys. So the first scenario is when you change the signing key prematurely. What this means is that your monitoring either did not catch some of the verifiers, which did not still get the new public key B. So here you probably left behind some stragglers where the verifier is still on the old key, and your certificate is now, your new certificates are now signed with the key B, but the verifier still doesn't trust it. At this point, those two services cannot talk to each other. So this is one scenario where there could be an incident here. And the second scenario is a premature distrust of the old public key, or like key revocation, so to speak. So you remove the the public key B from the trust bundles. So the verifiers no longer trust that key, but you left behind some certificate that did not rotate over to the new certificates. So which means the verified freshness of certificates had some, let's say there was a bug, you couldn't catch these stragglers which have old certificates. So once again, those services cannot communicate. You have an incident at that point. So how do we prepare for this? Every state transition here will need to have rollback capability. Let's say you prematurely pivot to a new private key, you must be able to roll back seamlessly into the old key so that you still have the verifiers trusting both A and B, so it should be safe to roll back at that point. And like I mentioned, the state changes need to be idempotent, so it should be an all or nothing state change, so there shouldn't be half-baked state left behind. And continuous improvement of safety signals is very important here, and that can only happen if you're continually testing your pipeline, particularly when your fleet is expanding, you're adding new hardware, new services, which are not probably into your monitoring pipeline. That's going to make it hard whenever there's an incident and they're left behind in the monitoring, which is hooking into your state changes. The third pattern is talking about availability and tiered SLOs. So we talked about the different rotations. Obviously, they are of different flavor. Although you're doing the same key transitions, they are of a different flavor in terms of the speed and the SLOs that we just mentioned in a few slides back. So the periodic hygienic rotations, so to speak, are routine and slow roll, and so conservative SLOs are important here, and making sure there's no impact to production. And potentially zero customer impact, right? The customer should be pretty much it should be opaque to them. They're not able to really even know that the key rotation is happening at this point. Whereas for emergency or compliance reasons, it's like a knob you just push it, and the services need to be aware that this is happening, because it's potentially going to cause some outages, but you need to be resilient to non-critical outages versus critical outages. You don't want a security incident to trigger an availability incident. So it still needs to have SLOs, so to speak, but at the same time be resilient to non-critical services failing for some reason. So I'll quickly dive into how the pipeline can change for one versus the other. So first, looking into emergency rotation, the features here is basically that each step is rapid, but painfully reversible, because it's rapid because you're probably not doing some safety checks that you would do for hygienic rotations. And there's a potential impact on availability. Like I said, probably weaker SLOs for non-critical workloads, because you're going to push to safety at this point. And safety checks only for highly critical workloads, so that you don't bring down important services. And if there are misbehaving workloads in terms of stragglers that have not caught up to new certificates, The strategy here could be to quarantine them from production so that they're not holding up the key rotation, so to speak, because your monitoring signal is probably saying, hey, there are these services or like devices that have not caught up, and so I'm not able to proceed with the rotation. So at this point, you just quarantine them out, drain them, and proceed with the rotation at the point. Comparing that with a periodic/hygienic rotation, we should think about this as a long-running process. So each state change is potentially a cron job, right? So you have periodic key additions, basically governed by whatever compliance you're trying to meet. Let's say the key age needs to be 6 months, so these should run at that period essentially. So both all the steps, basically addition, distribution, and change of keys based on the monitoring data happen at a regular cadence. So here of course, we need to make sure there are high availability guarantees for almost all workloads, not just critical workloads per se. And you can be a little more conservative with the misbehaving workloads which are not catching up. Instead of like quarantining in the previous case, here we can just wait for them to be repaired, reinstalled, drained, and then catch up and then proceed with the rotation, so to speak. And the last pattern is regarding observability and audit trails. So like you saw in the pipeline we just went through, monitoring state is important for even making progress in the key rotation. So metrics are important just to even build the pipeline, but they're doing more than just that because you need an audit-ready architecture for both compliance requirements as well as to make sure that your incident response is captured correctly when you're auditing it. And so making sure that metrics and databases are based out of key identifiers, so you're able to answer all the questions in case of an incident or an audit. So it's important to maintain like the key identifiers, the timestamps, not just in your KMS, but also in the services that are using it for signing and for verification, so that you're able to answer these questions, right? What signing keys are in use? When were they created? When were they retired? How much percentage of the fleet is using, is trusting this public key X? And also particularly the certificate age, tracking that is important because you want to know, particularly in a fine-grained way if possible, so that you know if critical hardware and critical workloads are on fresh certificates, so to speak. The TLDR here is that metrics must prove the actual state of the security perimeter. So at whatever stage of the process you're able to accurately depict where the pipeline is, where the keys are, and what state each service is at. Excuse me. Yep, so we are trying to build a dual-use infrastructure here. So have a knob with the same pipeline that it is built for slow, deliberate compliance, but also works as a fast tool in an emergency, and leveraging automation to pivot between the two based on what you're trying to solve for. And the automation as well, like we just talked about, is for both negotiating risk for compliance purposes and also for maintaining verifiability while accelerating velocity during critical compromises. So we did also see the same design patterns working for some other non-cryptography pushes to the fleet. Think about all other kinds of high stakes auditable automation that are needed, right? I've given a couple of examples here, like pushing network changes throughout the fleet is also pretty much a state-driven workflow similar to the key rotation we just talked about. And where when there is a security critical kernel patch that needs to be rolled out, that was very similar to handling a key rotation incident because you want to make sure every machine is now on the latest kernel patch. So this is also very similar to the idempotent state changes that we're just talking about. I will just talk about the takeaways here that we want to see from this talk. We talked about the SRE challenges, specifically with the constraints with data sovereignty, as well as incident response, and aligning technical architecture with these mandates. And we saw how automation can be built for satisfying both compliance and also used as a tool for rapid response. And we talked about risk minimization, so deploying automated pipelines for high impact rotations, and making sure that there's minimal human involvement, which is not just to reduce toil, but also for reducing the vulnerability window. And we also talked about monitoring and observability, how we can implement continuous monitoring for transactional integrity as well as for audit purposes. So I just want to call out that the goal is to shift from static compliance to dynamic verifiable security that scales with infrastructure velocity. So this is basically secure by design pattern. This turned out to be hard for long-running services, a fleet that's really old, like the Google data centers. But moving towards provable compliance is getting critical by the day. And that is my talk. We can take questions at this point.